All right, I am back with, I guess, the part two of this topic. I'm just going to be doing some examples of, part two of your assignment over this topic. So let's actually cut over to the assignment itself. Read these directions here. We'll talk about how we can apply what we learned last time to help us tackle these problems here. So we have sort of three steps here, or three bullet points. Directions: construct the structural formula for each of the covalent compounds. Okay, this is something that we've done already. Okay, constructing the structural formula. That means drawing the structure, right? Using all of those rules that we've learned in the past. Secondly, determine if any of the bonds are polar covalent bonds based on the difference in electronegativities. So that's bringing in what we did last time, right? Looking at the difference in electronegativity amongst all of the elements. Well, across all of the bonds, I should say. You'll see when I get into the examples what I mean. And look to see if any of the differences in electronegativity across any of the bonds are large enough to be polar covalent bonds, okay? And then if you do have polar covalent bonds, label them, okay? Label any polar covalent bonds appropriately with any partial positive or negative regions, okay? So let me hop over here to the slides. I have a couple more problems down here that I haven't done, so I'm going to do those right now, okay? And let's start with a basic one, okay? Right here, CH4, okay? That sounds good to me. So let me do a whiteboard here. This should work. Okay, so CH4. Step one in the directions is to construct the structural formula. Okay, so I'm going to put 1 carbon, 4 hydrogens. This is pretty involved, right? We have to remember to look up those valence electrons. Carbon has 4, hydrogens each have 1. And then we have to remember sort of, how to do the sharing of the electrons, right? We know that carbon wants to have 8 based on the octet rule. Hydrogen only wants to have 2, right? Hydrogen is that one exception, only wants 2 electrons. So we can just share 1 time each with each hydrogen here, and we can accomplish both of those goals. The carbon has 4 covalent bonds here, so it's got a total of 8 electrons, right? Each bond represents 2 shared electrons, and each hydrogen is also good to go, right, with just 1 bond. Okay, now I'm sort of assuming that all of these are going to be either covalent or polar covalent bonds, and that is true. Okay, so none of the problems that you're going to be working on today are going to be ionic bonds. All of them are going to be covalent. The question is, are these covalent bonds, are they just regular covalent bonds, or are they polar covalent bonds? And that's where you have to go back and look at those electronegativity values, specifically the difference in electronegativity, okay? So let me label this with a different color here. Let me go to blue. The electronegativity values for these elements are as follows. Hydrogen is at 2.1, and carbon is at 2.5, okay? So the difference in electronegativity across this bond, a carbon to a hydrogen, the difference in electronegativity is 2.5 minus 2.1. It's equal to 0.4, okay? And if you think back to the table that's in the slides up here that I'm not going to switch to right at this moment, but if you remember what the information was on those slides, if you have a small difference in electronegativity, what that means is that neither atom is significantly better at pulling on electrons than the other. So if you have a small difference in electronegativity, then your bond is just going to be regular covalent. Okay, it's not a polar covalent bond, it's just regular. Okay, and all 4 of these bonds are identical, right? They're all carbon to hydrogen. So what this means is that this is actually my final picture. I don't have any polar covalent bonds. I don't have any additional labeling to do, okay? Which is good, right? Nice and easy. Okay, let's look at another example. Okay, and we're just going to do two. Let me see here. Yeah, let's do number 5. Okay, this is methanamine, CH3NH2, or you could say CH5N. Either way is a good. Either way is correct in terms of writing the formula. Let me go ahead and pull up another whiteboard here. Okay, so the formula was CH3NH2. The name was methanamine. All right, so remember this, right? Meth means 1 carbon. Amine means that we're going to have an amine functional group. Really sort of putting a lot of things together here at the end of the semester, aren't we? And remember that there's another way you could write this formula, right? You could write this CH5N, right? These are sort of equivalent to each other, okay? What this has done here, this is that condensed structural formula that gives you a clue as to what the actual structure is going to be. The amine group looks like this. Okay. And we know that R right there is a placeholder for the carbon chain. Meth means we have 1 carbon. So if I go in here and, oh no, how do I get my marker back? I always struggle with this here. Oh goodness, what have I done? This is so frustrating. It's like whenever you, oh, there we go, perfect. All right, so the R, right, is a placeholder for the carbon. So I put my carbon in there, my 1 carbon, and then we know that carbon has a total of 4 valence electrons, right? One of which is being used up in this carbon-nitrogen bond, so these others must go over to hydrogens. Okay? And then you can see where that formula comes from. CH3, this is like a methyl group, okay? And then the NH2, which is the amine group, right? And then you can put it all together for that sort of overall formula of CH5N. Okay, so here's the structure, right? That's just part 1. Okay, so a lot, not part 1, but that's the first step of the directions, okay, for each problem. A lot goes into it, okay? If you are really struggling with figuring out how to draw these things, just look it up, okay? I want you to be able to do it, but I don't want you to get hung up on the assignment and like not make any progress because of that. So if you need to, like I'm going to give you the names of these compounds, look them up, Google them, draw them out, and then do the next 2 steps, you know, which are a bit simpler, okay? So the next thing we need to do is we need to look at these different elements here, look at all the different bonds, and figure out if any of them are polar covalent bonds, okay? So let me go ahead and put my electronegativities on here. All the hydrogens are 2.1, okay? And nitrogen is 3.0. I guess I can label these on here. It's not a big deal. Okay. We already determined in the previous problem that the carbon-hydrogen bonds are going to be regular covalent. Okay, the difference in electronegativity there is not big enough to fit into that moderate category, right? We're looking for a difference in electronegativity that is greater than or equal to 0.5, but also less than or equal to, I think it's 1.6. Okay, these are kind of arbitrary cutoffs, but that's what we're going to use for now. Okay, so we're looking for differences in electronegativity that are bigger than or equal to 0.5. Okay, so I've spotted 2 of them. Okay, and I'll use a slightly different color here. Let me go to this dark red. Okay, this bond between the carbon and nitrogen, the difference in electronegativity there is 3.0 minus 2.5. This is 0.5. That fits, okay? That fits into that moderate category. That means that the bond between carbon and nitrogen is a polar covalent bond. It's not a regular covalent bond, it's a polar covalent bond, meaning that the electrons, these 2 electrons here, that are that covalent bond, that's what the covalent bond is it's shared electrons. Those 2 electrons are not being equally shared between carbon and nitrogen. they in fact are being pulled slightly closer towards nitrogen because nitrogen has the higher electronegativity value. Okay, so we have identified a polar covalent bond. Okay, the element that has the higher electronegativity on that polar covalent bond is going to have a partial negative charge, and the atom that has the smaller electronegativity is going to have a partial positive charge. Okay, you can see how this is a little bit sloppy. I'm going to redraw it for you at the end. Okay, cleaned up a little bit. Okay, now we've covered all the bonds except for the nitrogen-hydrogen bonds. So these two bonds here, it looks like these are going to be polar covalent as well, because the difference in electronegativity here is 3.0 minus 2.1, so we have an even greater difference, right? 0.9. Once again, nitrogen is the higher, has the higher electronegativity value, so the covalent bonds here are not equally shared. These electrons are being pulled closer towards the nitrogen, which means the hydrogens are going to be the partially positive ones. The partial negative that we had from the carbon-nitrogen bond, we can just keep that there, okay? Because that nitrogen is still going to be the partially negative region, or partially negative atom, okay? So let me draw let me just clean this up a little bit for you, okay? Your final answer for this one should be something like this, okay? There's my structure, and then I want to tack in the partial positive. Remember that little symbol is a lowercase Greek letter delta, okay? It looks kind of like a music note. Okay, so I've got my 3 partial positives and then my partial negative, okay? This is what I'm looking for right here, okay? You do not have to do all this additional labeling. I was doing that for instructional purposes, okay? All right, so hopefully those two examples help. We can obviously work with this a little bit more during class, but if you watched this video ahead of time, you should be in a good position to be able to complete the assignment during like the asynchronous time, not have to work on this over the weekend or anything like that. Okay? All right. Thanks for watching, and I'll see you guys in class.